A giant storm on Neptune just vanished without a trace. Far out in the frozen dark, the solar system's windiest planet is a deep blue marble of mystery, and its most dramatic features are these fleeting, Earth-sized dark spots that appear and disappear like cosmic ghosts. By the end of this, you will understand how cutting-edge technology is letting us solve this planetary puzzle in real time. We will uncover why these monstrous storms vanish into thin air and what they reveal about the chaotic climate of a distant world. This is a deep space detective story, and the clues are changing right now. What does it feel like to watch a planet's personality shift from 4 billion kilometers away? These dark spots are not mere blemishes on Neptune's face. They are planetary-scale hurricanes, vast engines of weather that dwarf our own planet. Imagine a vortex of winds so powerful it could swallow our entire world whole and still have room to churn. That is precisely what we are looking at. These are anticyclonic storms, meaning they rotate in the opposite direction to the planet's spin, creating a high-pressure system that rises up from the deep, frigid layers of Neptune's atmosphere. In that way, they share a family resemblance with the most famous storm of all, Jupiter's Great Red Spot, but the similarity ends there. Jupiter's giant is an ancient, permanent fixture, a raging tempest that has lasted for centuries. Neptune's dark spots are cosmic mayflies. They appear, blaze with fury for a few Earth years, and then vanish without a trace, leaving the serene blue haze as if they were never there at all. Against the brilliant, sunlit blue of Neptune's methane-rich sky, they appear as deep, dark ovals like holes punched into the fabric of the planet. Their darkness is a chilling clue, suggesting they are not clouds themselves, but windows opening into a deeper, darker layer of the atmosphere far below the bright haze we usually see. To stand on the edge of one would be to peer into an abyss, a swirling void of unimaginable winds, all contained within a shape larger than our own home planet. Their fleeting existence is the central mystery. Why does Neptune, a world so far from the sun's warmth, birth such colossal and transient violence? Our first real encounter with this phenomenon came from a lonely robotic explorer. In 1989, the Voyager 2 spacecraft, having already toured Jupiter, Saturn, and Uranus, made its final planetary flyby at Neptune. What it saw there stunned everyone. The serene blue world was a maelstrom. A colossal dark oval nearly as wide as Earth dominated the southern hemisphere. This was the Great Dark Spot. Voyager's instruments clocked the winds screaming around its edges at over 1,200 miles per hour, the fastest ever recorded in the solar system. And right beside it, a smaller, fast-moving white cloud dubbed the Scooter zipped around the planet every 16 hours, a frantic companion to the giant vortex. This was not a quiet, frozen world. Neptune was alive with a violence and energy that seemed to defy logic given its vast distance from the sun. The Great Dark Spot became an icon, the face of a newly understood turbulent giant. But then it was gone. Just 5 years later, when the Hubble Space Telescope turned its gaze to Neptune in 1994, the spot had completely vanished. No trace, no fading remnant, just the unbroken blue. This was the moment the mystery crystallized. These were not permanent features like Jupiter's ancient storm. They were eruptions. Something deep within Neptune was cooking up these planet-sized hurricanes and then, just as suddenly, swallowing them back down. The Great Dark Spot's dramatic appearance and total disappearance framed the essential question we are still trying to answer today. What force creates a storm that can swallow Earth, and what hidden process makes it vanish without a scar? Hubble's sharp eye became our new window into this distant drama. After Voyager's brief flyby, the telescope took over the long-term watch, its position above Earth's blurring atmosphere giving us a clarity we had never possessed before. And what it showed was a world in constant churning flux. In the mid-1990s, it found the Great Dark Spot gone, but by 1995, a brand new dark spot had erupted in Neptune's northern hemisphere. It was a revelation. These were not one-time flukes. They were a recurring feature of the planet's chaotic climate, like a seasonal hurricane that appears, rages, and dissolves on a schedule we could not yet read. Hubble's observations over the next 2 decades painted a picture of a planet that is anything but serene. Dark spots would bubble up from the deep, linger for a few Earth years, sometimes migrating dramatically across latitudes and then simply fade away. We were no longer looking at a single mystery storm. We were watching a planetary weather pattern in action, a fundamental rhythm of this blue giant's atmosphere. The scale is almost impossible to grasp. These are not passing squalls. Each dark spot is a stable, organized weather system larger than our entire planet, yet on Neptune, they are as transient as a summer thundercloud on Earth. This creates a profound disconnect for us as observers. We are trying to understand a climate that operates on a timeline and with an energy we have no local experience with. We have centuries of recorded weather patterns for our own world. For Neptune, we have only a few fragmented snapshots across decades, like trying to predict Earth's entire climate history from a handful of storm reports written in the 1800s. Every new image from Hubble is not just a picture. It is a crucial data point in a slow-motion film, helping us piece together the life cycle of a storm that lives and dies in the deep freeze of interstellar space. Then, in 2018, Hubble delivered a stunning new chapter in this story. Astronomers spotted a colossal new vortex, a dark spot so vast it earned the title of the Northern Great Dark Spot. It was a breathtaking confirmation that the planet's fury was not a thing of the past. This new storm was churning in Neptune's northern hemisphere, a sprawling, in-Chi oval spanning roughly 7,600 miles across. To put that in perspective, that is wider than the entire continent of Asia. But this dark spot held a brilliant secret. For the first time, Hubble's advanced cameras captured a remarkable detail. The vortex itself was a deep, dark pit, but its edges were lined with dazzlingly bright, high-altitude clouds. These were not the soft, hazy methane clouds of the main atmosphere. These were compact, crystalline clouds of methane ice, shining like frozen neon signs tracing the outline of the storm. They formed as the furious winds of the dark spot forced gases upward to colder, higher altitudes where they condensed into these brilliant white caps. It was a beautiful and violent contradiction, a dark abyss framed by a crown of light. The detection of this new giant sent a wave of excitement through the astronomical community. It was not just another data point, it was proof. We were catching a great dark spot in the act, witnessing the birth and life of one of these legendary storms. This showed beyond any doubt that these were not random flukes or one-time anomalies from the Voyager era. They are part of a fundamental, recurring cycle in Neptune's chaotic climate. The planet has a rhythm, a heartbeat of colossal storm formation that we are only beginning to map. The Northern Great Dark Spot became a living laboratory, a chance to study the entire life cycle of one of these monsters from its powerful middle age. Its very presence asked the next urgent question. If we now know these storms are born and live with such ferocity, what mysterious force finally makes them die? The brilliant white clouds framing that dark vortex are not just a beautiful detail. They are a critical clue, and seeing them at all is a triumph of human ingenuity. To monitor the weather on a world 4 billion kilometers away, we cannot simply point a camera and hope for the best. Neptune's deep blue atmosphere is a uniform, hazy veil. To peer through it and spot the structure of storms, astronomers must become cosmic detectives, using light itself as their fingerprinting tool. This is where spectroscopy and precision engineering turn a blur into a detailed weather map. The Hubble Space Telescope uses special filters that act like super-powered sunglasses, blocking out most of the light and only letting through very specific colors or wavelengths. For Neptune, the most revealing filters are in the blue and the near-infrared parts of the spectrum. The blue filter captures the sunlight reflecting off the high-altitude methane haze, showing us the planet's overall shape and those bright companion clouds. But the near-infrared filter is the real magic. Methane gas in Neptune's atmosphere absorbs this type of light fiercely. So, where the atmosphere is thick and hazy, it looks dark in the infrared. But a deep, dark spot is a hole in that upper haze, a window to a deeper, warmer layer. That warmer layer glows with infrared light which shines up through the hole. To Hubble's infrared eye, the dark spot is not dark at all. It appears as a bright feature against a dark background. By combining these two views, the blue and the infrared, we get a complete three-dimensional picture. We see the bright high clouds and the deep structure of the storm simultaneously, a layered portrait of atmospheric violence. This cosmic surveillance has now gotten a powerful upgrade from the ground. The newest generation of ground-based telescopes, like the Keck Observatory in Hawaii and the Very Large Telescope in Chile, are equipped with a revolutionary technology called adaptive optics. Here is the problem. Earth's atmosphere is turbulent, constantly blurring and distorting the light from stars and planets, which is why stars twinkle. For centuries, this made ground-based views of planets fuzzy and limited. Adaptive optics solves this with a stroke of genius. The system uses a powerful laser to create an artificial guide star high in the atmosphere. Sensors monitor how this fake star's light is distorted by atmospheric turbulence, and then, up to 1,000 times per second, a computer commands a flexible mirror to warp and bend in the exact opposite way. It cancels out the blur in real time. The result is a view from the ground that can rival and sometimes surpass the clarity of Hubble in space. These giant ground-based eyes, now unshackled from atmospheric blur, can capture incredibly sharp images of Neptune's fleeting storms. They provide more frequent observations, filling in the gaps between Hubble's scheduled looks. We are no longer relying on a single sentinel in orbit. We have built a global network of intelligent eyes, both on the ground and in space, all trained on that distant blue dot. This coordinated watch is what allows us to track a storm's migration, measure its winds, and finally witness its demise. It transforms astronomy from taking occasional snapshots to broadcasting a continuous planetary weather report from the edge of the solar system. The technology itself is a silent protagonist in this story. Every clear image of a vanishing storm is a victory of precision optics, computational power, and human curiosity over the unimaginable distances of space. But what is the actual recipe for brewing a storm this big? To understand that, we need to look at the ingredients churning inside Neptune's deep blue atmosphere. The planet is not a solid rock like Earth or Mars. It is a gas giant, a world with no real surface to speak of, just an atmosphere that gets denser and hotter the deeper you go until it eventually merges into a slushy, superheated ocean of water, ammonia, and methane ices. The outer layers we see are mostly hydrogen and helium, the same fundamental gases that make up the Sun. But it is the third ingredient, methane, that gives Neptune its stunning identity and its most violent weather. Methane gas in the upper atmosphere absorbs red light from the distant sun and scatters blue light back into space, painting the entire planet that iconic deep azure. This methane also condenses, forming a pervasive high-altitude haze of methane ice crystals. Think of this haze as a brilliant blue blanket shrouding the entire planet. A Neptune dark spot is essentially a tear in that blanket. It is a colossal gap in the upper cloud deck, a clearing that opens a window down to a deeper, darker, and warmer layer of the atmosphere. From our distant vantage point, that hole looks like a dark oval because we are seeing the absence of the reflective, bright blue haze. We are staring into the planet's shadowy interior. So the storm is not the dark spot itself. The dark spot is the result of the storm, the scar it leaves on the sky. The real engine is the vortex, a massive high-pressure system spinning in the opposite direction to the planet's rotation. As this anticyclone churns, its powerful dynamics somehow push the bright methane haze aside or prevent it from forming, creating that clear window. The physics at play are intense. Deep in Neptune's atmosphere, where pressures are thousands of times greater than on Earth, gases are forced upward. As they rise, they expand and cool. If the conditions are just right, different chemicals condense at different altitudes, creating distinct layers of clouds. The dark spot vortex seems to disrupt this orderly layering. It acts like a giant atmospheric mixer, creating a local environment where the high-altitude methane ice cannot persist. Imagine a pot of water boiling on your stove. The rolling bubbles create clear patches in the otherwise frothy surface, letting you see the darker water below. A Neptune dark spot is a planetary version of that phenomenon, a bubble of different atmospheric chemistry so vast it creates a hole in the sky. The energy to power this does not come from the weak sunlight, which is 900 times dimmer than on Earth. It must come from within, from the fierce heat still radiating from the planet's molten core, left over from its violent birth 4.5 billion years ago. This internal furnace, not the distant sun, is the true powerhouse driving those supersonic winds and cooking up storms large enough to swallow our world. This very transience is the heart of the mystery. Why do these planet-sized hurricanes, once born, simply fade away into the blue? Solving a crime scene 4 billion kilometers distant means piecing together clues from fleeting glimpses, and scientists have developed some compelling theories for the Great Vanishing Act. One leading idea involves a perilous planetary migration. On Earth, hurricanes are steered by atmospheric currents and often fizzle out when they move over land or into cooler waters. On Neptune, the danger zone might be the equator. As a dark spot forms, it can drift across the face of the planet, pushed by immense jet streams. If one of these vortices wanders too close to the equatorial region, it might encounter a fundamentally different atmospheric environment. The wind shear, the change in wind speed or direction with altitude, could become too extreme. Think of it like trying to keep a spinning top upright on a surface that is itself tilting and shifting unpredictably. The organized, tight rotation of the storm could be torn apart, its energy dissipated into the chaotic background flow of Neptune's atmosphere. The storm doesn't land because there is no land. Instead, it hits a wall of invisible turbulence and simply unravels. Another possibility is that these storms are inherently finite. They are powered by heat rising from Neptune's deep interior, and they might have a limited fuel supply. Like a candle burning at both ends, the vortex could slowly exhaust the energy that sustains its structure. The fierce winds that define it might begin to falter, allowing the bright methane haze to seep back in and fill the dark window. The hole in the sky patches itself over, and the storm vanishes from view, its energy dissipated as subtle warmth in the vast atmosphere. It is also possible that Neptune's supersonic winds, the fastest in the solar system, act as a relentless shredder. Even a storm the size of Earth is not immune to being pulled and stretched by faster-moving streams around it. Over several Earth years, this constant shearing force could distort the vortex, breaking its cohesion until it is nothing more than a faint ripple in the deep blue. The profound challenge is that we are trying to understand a process that unfolds over a period of years, using observations separated by months. It is like trying to document the entire life of a giant sequoia tree by looking at it for 1 minute every few weeks. We might catch it in spring bloom, in summer fullness, and in autumn color, but we could easily miss the exact moment a major branch falls in a winter storm. For Neptune, every clear image from Hubble or a ground-based telescope is that precious 1-minute look. We have seen dark spots appear, we have watched them migrate. We have seen them gone in the next observing window, but we have never directly witnessed the death throes of one of these giants. The final act, the precise mechanism of dissolution, remains hidden in the gaps between our snapshots. This makes every new observation a potential key. Astronomers are on constant watch, hoping that the next time they point their telescopes at the blue giant, they will catch a dark spot in its final days, visibly distorting or shrinking. That single, fleeting image could be the Rosetta Stone that decodes the entire life cycle, telling us exactly what cosmic forces finally silence a storm larger than our world. The supersonic winds that race around Neptune are not just a backdrop for the dark spots, they are the very fabric of the planet's chaotic existence. These are the fastest planetary winds in our entire solar system, screaming around the equator at speeds that can exceed 1,200 miles per hour. To put that in perspective, that is more than twice the maximum wind speed inside the most powerful tornado ever recorded on Earth. On Neptune, that is just the baseline weather. This incredible velocity creates a fundamental puzzle. The Sun at that distance is a tiny, faint dot providing only a whisper of warmth. It cannot possibly generate that kind of atmospheric fury. So where does the energy come from? The answer lies deep within the planet's heart. Neptune is still glowing with the fierce heat of its own creation, the leftover thermal energy from the violent collisions and gravitational compression that formed it over 4 billion years ago. This internal furnace is the true powerhouse. Heat from the molten core rises through the slushy, exotic ocean of superheated ices and into the gaseous outer layers. That rising heat sets the entire atmosphere in motion, like a pot of water boiling on a cosmic stove. The temperature difference between the warm interior and the frigid outer space is the engine that drives those supersonic jet streams. This creates a fundamental difference from Earth. Our weather is a thin, sun-driven skin on the surface of a rock. Neptune's weather is a planet-wide, deep-seated churn, a manifestation of the giant's slow cooling and its relentless release of primordial energy. It is a world powered from the inside out, and its winds are the visible signature of that deep planetary heartbeat. These ferocious winds do not blow in a simple, uniform stream. They are organized into broad bands like latitude lines of pure velocity, racing in alternating directions. It is within this violent, structured flow that the dark spots must live and die. The interaction between a massive, rotating vortex and these supersonic rivers of air is what likely defines a storm's entire lifespan. Imagine a giant, slow-spinning eddy caught in the path of a jet stream moving at over 1,000 miles an hour. The winds shear and stretch the storm, constantly testing its structural integrity. A dark spot might form in a relatively calm zone between two opposing jet streams, a pocket of stability where a vortex can organize. But as it drifts, it can be captured by one of these immense rivers of air and dragged along. If the storm moves into a region where the wind shear is too extreme, the differential forces can literally tear it apart, pulling its swirling mass into long, dissipating streamers. Alternatively, the vortex might fight the current, maintaining its rotation for years, until it either exhausts its internal energy or wanders into a fatal atmospheric trap. This creates a dynamic and violent atmospheric lifestyle for the blue giant. The dark spots are not isolated events. They are temporary features born from and ultimately consumed by the planet's overwhelming atmospheric circulation. They are like massive whirlpools that form in a raging river, impressive and powerful in their own right, but always at the mercy of the greater, faster current that surrounds them. Their transience is not a flaw, it is a direct consequence of living in an environment of such unimaginable force. Neptune does not have calm weather that is occasionally interrupted by a storm. For this world, the supersonic wind is the constant, the permanent state. The dark spots are the fleeting interruptions, the moments when the planet's internal heat manages to organize itself into a recognizable, colossal structure before the endless, screaming winds reclaim their dominion. To bridge the gap between those fleeting snapshots, scientists have built entire Neptunes inside supercomputers. This is where the mystery moves from the telescope's lens into the realm of digital physics, where we can run experiments that are impossible across 4 billion kilometers of space. Researchers feed every scrap of data from Hubble, Keck, and Voyager into immensely complex mathematical models that simulate the churning fluids and heat dynamics of a gas giant's atmosphere. These are not simple animations, they are rigorous digital laboratories governed by the fundamental laws of physics. Inside them, virtual storms can be born, live, and die 1,000 times over, allowing us to test every theory about their disappearance. The process starts with the known framework of Neptune's conditions: the supersonic wind bands, the temperature gradients, the composition of gases, and the intense internal heat flow. The model then sets this virtual atmosphere in motion and watches what emerges. Often, without any direct command to form a storm, the simulation will spontaneously generate massive, dark vortex structures from the chaotic flow. It is a breathtaking validation, a sign that the models are capturing something real about the planet's fundamental nature. These digital storms behave in eerily familiar ways, migrating across latitudes, developing bright companion clouds, and eventually, under the right conditions, breaking apart. This lets scientists play with variables we cannot control in reality. They can crank the wind shear up to impossible levels to see how quickly a vortex shreds. They can dial down the internal heat source to see if the storms lose their power. They can even hit pause and rewind, dissecting the exact moment a simulated dark spot begins to unravel. One pivotal finding from these simulations points directly to the equator as a storm graveyard. As a digital vortex drifts toward Neptune's midsection, it encounters opposing jet streams and intents shear that stretch and distort its rotation. The model shows the once tight oval being pulled into a long, thin filament before its energy dissipates completely into the background turbulence, leaving no trace. This digital demise matches perfectly with the observational fact that we have never seen a dark spot cross the equator. They always vanish before they get there. The supercomputer becomes a time machine, filling in the missing frames between our real-world snapshots and revealing the invisible forces that silence these giants. It represents a profound fusion of disciplines where data science breathes life into planetary science, allowing us to witness the full, violent life cycle of a storm on a world we may never physically touch. The most famous storm in the solar system offers a stunning contrast to Neptune's phantoms. Jupiter's Great Red Spot is a monument of permanence, a swirling crimson eye that has watched the solar system for at least 350 years and possibly much longer. It is a storm so ancient it was first glimpsed by telescopes in the 1600s. If Neptune's dark spots are like sudden, violent summer thunderstorms, Jupiter's spot is the eternal hurricane, a fixed landmark in a turbulent sky. This stark difference in longevity points to a fundamental divergence in how these two gas giants operate. Both storms are anticyclones, both are wider than Earth, yet one endures for centuries while the other vanishes in a handful of years. The secret lies in what feeds them. Jupiter's Great Red Spot is a high-altitude storm rooted in the upper layers of the atmosphere. It is sustained by a complex dance of smaller storms that merge into it and by the energy of Jupiter's powerful internal heat, but crucially, it seems to be trapped between two of the planet's strongest jet streams. These act like immovable atmospheric walls, corralling the storm and preventing it from drifting into destabilizing regions. It is a prisoner of its own power, locked in a stable zone where it can spin indefinitely, fed by the chaotic weather around it. Neptune's dark spots face no such protective custody. Their atmosphere is a realm of even more extreme wind shear and deeper, more violent energy transfer. They are not prisoners but nomads drifting through a supersonic landscape that eventually tears them apart. The energy source is different too. While both planets are powered by internal heat, Neptune's greater distance from the Sun means its atmospheric dynamics are almost entirely driven from within, with less influence from solar heating. This creates a more chaotic, bottom-up churn where large structures struggle to maintain coherence. Think of it like two different oceans. Jupiter's atmosphere might be like a deep sea with a strong, stable current that can maintain a massive, permanent whirlpool for ages. Neptune's is like a shallow, violently churning surf zone, where even a huge wave crashes onto the shore and dissipates in minutes. The fleeting nature of Neptune's dark spots is not a sign of weakness, but a testament to the sheer, unruly violence of its climate. Jupiter built a storm that became a permanent fixture. Neptune's atmosphere is too wild for that, constantly creating and destroying its own titans, reminding us that even among giants, there are profound and beautiful differences in temperament. That brilliant blue color is more than just a pretty facade. It is a chemical reaction unfolding on a planetary scale. The key ingredient is methane, a simple molecule of carbon and hydrogen that acts like a cosmic filter. Sunlight, even from our distant, feeble stars, streams into Neptune's upper atmosphere. When photons of light strike methane molecules, something specific happens. The red wavelengths are absorbed, while the blue wavelengths are scattered back out into space. This process, called Rayleigh scattering, is the same reason our own sky is blue. But on Neptune, with a much thicker methane-rich atmosphere, the effect is amplified into that deep, uniform azure. But sunlight does not just bounce off, it also breaks things apart. This is where photochemistry takes over. The same ultraviolet light that gets filtered is powerful enough to tear the methane molecules apart. The fragments then recombine into more complex hydrocarbons like ethane and acetylene. These heavier molecules condense into tiny, frozen particles, forming a global blanket of photochemical haze. This haze is not a thick cloud, but a diffuse, high-altitude smog of complex organic compounds that contributes to the planet's overall brightness and its smooth blue appearance. It is a perpetual, slow-motion factory, using sunlight to transform simple gas into a mist of frozen hydrocarbons that shroud the entire world. So when we look at Neptune, we are not seeing a solid blue surface. We are seeing this photochemical haze, a glowing, scattered layer that hides the turbulent depths below. A dark spot, then, is a tear in this veil. It is a window where this high-altitude haze has been cleared away or is dramatically thinner, allowing us to peer down into a darker, warmer atmospheric layer that does not scatter blue light. The vortex of the storm itself seems to create conditions that prevent the haze from forming or that actively push it aside. This could be due to sinking air in the center of the high-pressure system, which would suppress cloud formation, or due to the intense winds shearing the haze particles away from the vortex's core. The dark spot is not an object, it is an absence, a clearing in the photochemical fog. This creates a fascinating possibility regarding the storm's visibility and even their formation. Neptune, like Earth, has seasons, each lasting over 40 Earth years due to its long orbit. As the planet slowly orbits the Sun, different hemispheres receive slightly varying amounts of sunlight over these decades-long cycles. Could this seasonal change in solar energy influence the photochemical factory in the sky? It is a compelling thought. When a hemisphere tilts toward the Sun, the increased ultraviolet light might accelerate the production of this hydrocarbon haze, potentially making the atmospheric blanket thicker and more uniform. Conversely, during a hemisphere's long winter, haze production might slow. If the haze is the canvas, then changes in its thickness could affect how easily a storm can punch a dark hole through it, or how visible that hole becomes to our telescopes. A storm forming under a thin haze might create a more pronounced, darker spot. One emerging under a thick, global smog might be harder to detect, or it might struggle to clear such a dense layer. This introduces a subtle, cyclical rhythm to the entire mystery. We are not just watching storms come and go at random. we might be witnessing a complex dialogue between the planet's internal heat, which drives the winds and forms the vortices, and the external touch of sunlight, which paints the backdrop against which these dark dramas play out. The visibility of Neptune's most violent features could hinge on the slow, patient chemistry of its sky. Neptune's long, slow dance with the distant sun adds another layer of rhythm to this chaotic climate. The planet is tilted on its axis by about 28 degrees, very similar to Earth's 23-degree tilt. This familiar geometry creates seasons, but on a timescale that dwarfs our own. A single year on Neptune lasts 165 Earth years, which means each season from solstice to solstice stretches for roughly 4 decades. Picture a seasonal cycle where spring itself lasts longer than most human careers. For 40 Earth years, one hemisphere leans gradually toward the faint sun, receiving a tiny but consistent increase in solar energy, while the other hemisphere sinks into an equally long winter twilight. The change is minuscule in absolute terms. Sunlight at Neptune is 900 times weaker than on Earth, but in an atmosphere powered from within, even a whisper of extra heat from above could act as a subtle trigger. This seasonal sunlight does not power the supersonic winds that comes from the interior furnace, but it could influence where and how that internal energy manifests. Think of it like a giant, slowly tilting pot on a stove. The burner underneath, the planet's internal heat, provides the roaring boil, but if you tilt the pot ever so slightly over decades, the hottest, most active bubbles might start to rise more on one side than the other. The seasonal sunlight could gently warp the temperature gradients in the upper atmosphere, potentially steering the massive circulation patterns or influencing the stability of different latitudes. It might create atmospheric zones that are temporarily more or less hospitable for a giant vortex to form and sustain itself. Could the appearance of a great dark spot be a seasonal event? It is a compelling, patient hypothesis. If the formation of these storms is tied to the precise alignment of internal heat flow and upper atmospheric conditions, then the decades-long shift in solar heating might set the stage. Perhaps the northern hemisphere becomes more prone to spawning these dark vortices during its long summer, when the slightly increased sunlight alters the chemistry and dynamics of the high-altitude haze. The dramatic appearance of the northern Great Dark Spot in 2018 did coincide with the Northern Hemisphere's summer, a season that began in the early 2000s and will last until the 2060s. This is not proof, but it is a fascinating clue written across a timeline we can barely comprehend. For us as observers, this introduces a profound challenge of patience and perspective. To even begin testing this seasonal hypothesis requires monitoring Neptune consistently for longer than the Hubble Space Telescope has existed. We have less than one full Neptunian season of detailed observations. We are essentially trying to understand an entire climatic rhythm by studying a single beat of the drum. Every new dark spot we discover adds a crucial data point, but the full pattern, the grand cycle of storm activity across centuries, remains hidden in the future and the past. Our entire modern record of Neptune's weather is just a snapshot from one long, slow summer in the north. What happens as that hemisphere moves toward autumn over the next 20 years? Will the dark spots become less frequent, or will they migrate? The answers are unfolding in ultra-slow motion, requiring a kind of generational astronomy where the questions we ask today might be answered by telescopes and scientists not yet born. This transforms the mystery from a simple puzzle into a legacy, a cosmic story we are only beginning to read, one patient chapter every 40 years. This slow, seasonal rhythm was suddenly interrupted by a dramatic and unexpected turn. In 2023, the Hubble Space Telescope revealed something that sent a jolt through the astronomical community. A dark spot in Neptune's southern hemisphere, which had been behaving as predicted, abruptly changed course. It stopped its southward drift and began moving north, a sharp reversal that defied the expectations of every major atmospheric model. For years, our simulations had painted a consistent picture of these storms as passive drifters, carried along by the planet's dominant wind currents. Their typical southward migration in the southern hemisphere fit neatly into our understanding of Neptune's circulation patterns. This sudden U-turn was not just a minor course correction, it was a fundamental challenge to that understanding. The storm was not merely a passenger on the wind, it appeared to have a mind of its own, actively steering against the flow. This single observation forced a profound realization: our digital Neptunes, for all their sophistication, were still missing a crucial piece of the puzzle. The models could simulate the birth and death of these vortices, but they could not explain this autonomous, defiant movement. It was as if we had built a perfect model of ocean currents, only to watch a massive whirlpool suddenly reverse direction and swim upstream. The implication was clear: there are deeper, more complex forces at play within Neptune's churning blue depths than we had accounted for. Perhaps the storm's own immense rotation was interacting with the planet's deeper atmospheric layers in a way we do not yet understand, generating its own momentum. Or maybe there are hidden waves or currents far below the visible cloud tops that can tug on these giants, pulling them in unexpected directions. This surprising behavior did not break the story. It made the mystery richer and more urgent. It proved that Neptune's atmosphere is not just a violent place, it is an intelligently chaotic one, full of surprises that keep our models humble. Every time we think we have a handle on the blue giant's personality, it shows us a new facet of its turbulent soul. This keeps the narrative thrillingly current, reminding us that planetary science is not about solving static puzzles from the past. It is about observing a dynamic, living system that is actively writing its own rules 4 billion kilometers away. That surprising U-turn was spotted not by a billion-dollar space telescope, but by a network of dedicated watchers. The line between professional and amateur astronomy is blurring into a powerful new reality. Backyard observers, armed with technology once reserved for major observatories, are now joining the hunt for Neptune's secrets. With modern 14- and 16-inch telescopes, sophisticated adaptive optics systems, and sensitive planetary cameras, a committed amateur can now resolve Neptune not as a mere point of light, but as a tiny, distinct blue disk in the eyepiece. They can capture the subtle shading of its atmosphere and, under exceptional seeing conditions, even hint at the presence of a major dark spot or a bright companion cloud. This is not just stargazing, it is distributed planetary surveillance. Imagine a global network of these skilled observers, each in a different time zone, all trained on that same distant blue dot. While the Hubble Space Telescope can only look at Neptune for a few precious hours each year due to intense scheduling demands, and while large ground-based observatories face their own weather and scheduling constraints, this army of amateurs could provide something priceless: continuous coverage. One observer in Chile catches the planet as it sets in their evening sky, another in Australia picks it up as it rises hours later, and a third in North America follows it through the middle of the night. Together, they create a never-blinking eye on the solar system's outermost giant. This transforms planetary science from a series of isolated snapshots into something resembling a live broadcast. A sudden change in a dark spot's shape, a new bright cloud eruption, or the first signs of a storm's dissipation could be caught in real time, triggering an alert to the professional community to turn their most powerful instruments toward the event. It is a futuristic model of collaborative discovery, a lifestyle where anyone with passion and precision can contribute to a grand cosmic weather report. The data from a single backyard observation might be the crucial piece that connects two professional Hubble images, revealing the speed of a jet stream or the true rotation period of a vortex. This citizen science approach turns the entire planet Earth into a single, coordinated telescope, with its lenses spread across continents, all focused on solving the mystery of the vanishing storms. It democratizes the thrill of discovery, making the monitoring of an alien climate a shared human endeavor. the next great clue in Neptune's story might not come from a mountaintop or from orbit, but from a suburban driveway, a signal from the edge of the solar system captured by someone who simply loves to look up. The storm's unexpected U-turn is a puzzle we can see, but to solve it, we need to feel the atmosphere's hidden heat. This is where the investigation takes its next great leap forward into the infrared. The James Webb Space Telescope is not just another observatory. It is a thermal camera for the cosmos, designed to see the universe in the glow of heat rather than the glare of reflected light. For Neptune's dark spots, this changes everything. Hubble and our ground-based telescopes show us the shape and motion of these storms. Webb will reveal their inner fire. Its powerful infrared instruments can map the temperature variations within and around a dark spot with a precision we have never before possessed. Every swirl, every edge, every clear patch in the haze will have its own thermal signature. Is the center of the vortex warmer or colder than the surrounding winds? How does the temperature change across that brilliant crown of bright companion clouds? These are not just pictures, they are energy diagrams showing us where heat is rising from the deep and where it is being violently churned. The data will be a direct test of our computer models. Those simulations make specific predictions about the temperature structure of these anticyclones. Webb's actual measurements will tell us if our digital Neptunes are on the right track or if we have missed a fundamental source of energy. It can also detect the faint chemical fingerprints of molecules swirling in the storm. By analyzing the specific infrared light absorbed or emitted, Webb can identify not just methane, but trace amounts of other hydrocarbons and even measure the abundance of heavier elements like hydrogen sulfide. This lets us smell the storm. Is the air composition inside the dark spot different from the air outside? Does it carry a distinct chemical signature from the deeper layers it exposes? These clues will tell us how deep the vortex roots itself and how it exchanges material with the atmosphere below. Webb transforms our view from a two-dimensional weather map into a three-dimensional thermodynamic autopsy. We will no longer be guessing about the forces at play. We will be measuring them directly, watching the engine of the storm in action. This positions the telescope as the ultimate detective in the mystery of the vanishing giants. It will not just watch the storms, it will diagnose their health. By monitoring a dark spot over several of its Earth-year cycles, Webb could detect the subtle changes that foretell its demise. A slight warming here, a shift in chemical balance there. These could be the vital signs of a storm entering its final days. For the first time, we might not just discover a dark spot has vanished. We might understand why it was doomed weeks or months before it finally faded from view. The James Webb Space Telescope hands us the keys to a deeper layer of reality on that distant blue world, turning the invisible forces of heat and chemistry into a story we can finally read. But the James Webb Space Telescope is only the next step in a much grander vision. On remote mountain peaks in Chile and the Atacama Desert, the foundations are being laid for a new generation of ground-based observatories so colossal they will redefine our view of the cosmos. These are the extremely large telescopes, machines like the European Extremely Large Telescope and the Giant Magellan Telescope, with primary mirrors spanning over 30 meters in diameter. To grasp their scale, picture a telescope mirror wider than a professional tennis court, gathering starlight with an almost unimaginable hunger. For a faint, distant world like Neptune, this leap in power is transformative. Their immense light-gathering ability means they can capture sharper, clearer images faster, piercing the blue haze with a resolution we have only dreamed of. Where Hubble or Webb might see a dark spot as a single, distinct oval, these future giants could potentially resolve the storm's internal structure. We might see smaller, swirling eddies along its edges, the turbulent boundaries where the vortex meets the supersonic winds. We could track individual bright cloud formations as they develop and dissipate over days or weeks, watching the storm's metabolism in real time. This level of detail would turn a dark spot from a mysterious blob into a complex, dynamic ecosystem of weather, letting us study its anatomy the way a meteorologist studies the eye wall and rain bands of a hurricane. The goal is audacious: to move from taking snapshots of Neptune's climate to broadcasting a continuous weather report. With these telescopes coming online in the next decade, we could monitor the blue giant not just once a year, but over entire observing seasons, watching atmospheric features evolve from week to week. A dark spot's drift, its slow distortion, the first signs of its unraveling, all could be documented in a high-definition time-lapse spanning years. This persistent gaze would finally fill in the agonizing gaps between our current observations, revealing the continuous narrative of storm life and death. It promises a future where checking on Neptune's weather becomes a routine part of astronomical science, where students might analyze data showing a great dark spot's migration from the previous month, tracking its speed and health as it journeys across the frozen blue sky. These telescopes are not just bigger glass, they are time machines for planetary science, offering us a front-row seat to the slow, majestic, and violent weather of a world that has kept its secrets at the very edge of our sight for generations. The ultimate answer to Neptune's mysteries may one day descend through its violent blue skies. For all the power of our telescopes and supercomputers, there is a limit to what remote sensing can tell us. To truly understand the dark spots, we need to go there, to taste the air and feel the wind inside the storm itself. This is the dream of a direct mission, a spacecraft that makes the multi-billion-kilometer journey to become a temporary citizen of the blue giant's atmosphere. The engineering hurdles for such an endeavor are almost beyond comprehension. First, there is the sheer distance. A mission to Neptune would take over a decade to arrive using current propulsion technology, requiring a spacecraft robust enough to survive the cold and radiation of deep space for longer than some satellites have been in orbit around Earth. Its power source, likely a radioisotope thermoelectric generator, would have to provide reliable electricity for 15 years or more before it even begins its main work. Then comes the entry. Neptune has no solid surface, so an atmospheric probe would be designed to transmit data for as long as possible as it plummets through increasingly dense layers. But this is not a gentle descent into a calm sky. The probe would hit the outer fringes of the atmosphere at tens of thousands of miles per hour. A heat shield would have to withstand temperatures hotter than the surface of the sun, ablating away to protect the delicate instruments within. Once through the initial fire, it would deploy a parachute, but this is where Neptune's violence takes over. Those supersonic winds, the fastest in the solar system, would batter the descending probe with unimaginable force. The parachute and the probe itself would need to be engineered to survive not just the pressure and the cold, but being caught in a horizontal gale moving at over 1,000 miles per hour. It would be like trying to lower a scientific instrument by string into the heart of a permanent planet-wide hurricane. The goal would not be a soft landing because there is nothing to land on. The goal would be a controlled, data-rich fall into the abyss, transmitting every possible measurement until the increasing pressure and heat finally crushed and melted the probe into the atmosphere, becoming a permanent, minuscule part of the giant it came to study. The scientific payload of such a probe would be a suite of instruments designed to turn our biggest questions into hard numbers. Miniature mass spectrometers would inhale tiny samples of the atmosphere, instantly identifying the exact chemical soup at different altitudes, measuring the ratios of methane, hydrogen, helium, and trace hydrocarbons. This would tell us definitively what the dark spot is made of and how its chemistry differs from the surrounding air. Ultrasonic anemometers, essentially tiny wind gauges, would measure the wind speed and direction in 3 dimensions, feeling the true turbulence and shear that our telescopes can only estimate from afar. Pressure and temperature sensors would chart the environment in real time, building a vertical profile of the storm's thermodynamic engine. and crucially, a nephelometer would shine a laser beam into the haze, measuring how the particles scatter the light to determine the size and density of the aerosol particles in the photochemical smog and the storm's clearing. For a mission targeting a dark spot, the probe would ideally be released from an orbiter at the precise moment to ensure it descends directly through the vortex. Imagine the data stream for perhaps an hour as it fell through the towering walls of the storm. It would send back a direct diary of its journey. We would know the exact wind speed at the dark spot's edge. We would have a chemical fingerprint of the deep atmosphere it exposes. We would feel the pressure changes that define its structure. This single, sacrificial probe could provide more certain knowledge about Neptune's inner workings than a century of remote observation. It would transform the dark spot from a distant, puzzling image into a physical place with measurable properties, closing the loop between our brilliant speculation and beautiful, hard-won truth. Neptune is not just a solitary blue giant at the edge of our solar system. It is a prototype, a local laboratory for a class of worlds that fills our galaxy. When astronomers peer into the depths of space, hunting for planets around other stars, one of the most common types they find is not like Earth or Jupiter. It is the ice giant, a world with a size and composition eerily similar to our own Neptune. These distant Neptunes orbit stars light years away, appearing in our data only as a faint dip in starlight or a subtle wobble in a star's motion. The signals we receive are whispers, ghostly impressions of a world we will never see up close. To decode those whispers, to understand the climate and weather on an alien ice giant, we must first become fluent in the language of our own. Every mystery we solve about Neptune's dark spots, every law of atmospheric physics we confirm or challenge with its supersonic winds, becomes a Rosetta Stone for interpreting the faint clues from these exoplanets. Imagine a telescope, perhaps the James Webb or its successor, collecting the spectrum of light from a Neptune-like world 50 light-years distant. That spectrum is a barcode of chemicals and temperatures, a single, complex reading of the planet's entire atmosphere blended together. Without a local example to guide us, that barcode is almost meaningless, but with our hard-won knowledge from Neptune, we can begin to translate it. The detection of methane, the presence of high-altitude hazes, even the inferred temperature patterns, all these pieces of data find their reference point in the turbulent blue world we have been studying so closely. When we see an unexpected variation in an exoplanet's brightness over time, could that be a dark spot, a colossal storm like Neptune's rotating in and out of view? When our models suggest a certain wind speed based on temperature gradients, does Neptune's example tell us those models are correct or wildly off? The fleeting life and sudden death of a dark spot teach us about energy transport, about how heat from a planet's core moves through an atmosphere and manifests as weather. This process is universal. An ice giant orbiting another star will have its own internal furnace, its own complex chemistry, and its own version of storms. By meticulously documenting the life cycle of a storm on our Neptune, we are essentially writing the textbook on ice giant meteorology, a textbook we will use for centuries to come to read the skies of distant worlds. This transforms the entire endeavor from studying a single planet to developing a fundamental science of planetary atmospheres. The supersonic winds screaming around Neptune are not just a curiosity, they are a data point on how fluid dynamics operate under extreme conditions. The photochemical haze that paints the planet blue is a lesson in how starlight interacts with alien atmospheres. Each observation, each computer simulation, each theory tested against the blue giant's behavior adds a crucial paragraph to that textbook. The ultimate goal is breathtaking: to look at a single pixel of light from an impossibly distant world and confidently say, there is a storm there. The atmosphere is churning with deep-driven energy. The climate is chaotic, and here is why. Neptune's vanishing storms are more than a local mystery. They are the key that will one day unlock the secrets of 1,000 other blue dots scattered across the galaxy. turning faint astronomical signals into vivid stories of alien weather. That blue marble of churning mystery is more than a scientific puzzle. It is a work of art in motion, a testament to the staggering diversity of worlds that exist even within our own cosmic backyard. Every time a dark spot vanishes, it reminds us that the universe is not a static museum of fixed exhibits. It is a living, breathing gallery of dynamic processes, a place where entire planets have personalities and moods that shift over decades. Solving the mystery of Neptune's fleeting storms does more than fill a page in a textbook. It fundamentally reshapes our understanding of what is possible. For centuries, we looked at the outer planets as distant, frozen marbles. Now we know they are roiling, energetic worlds with climates as complex and violent as any on Earth, just operating on a scale and timeline we are only beginning to comprehend. This knowledge humbles us. Our own planet's weather, for all its power, is a local phenomenon. Neptune shows us that chaos and beauty are universal languages, spoken in supersonic winds and deep blue hazes across the light years. It quietly dismantles any assumption that our solar system is ordinary or fully understood. There are giants at our doorstep with secrets we are still deciphering. That pursuit, the patient piecing together of clues across generations, is a profoundly human act. It connects the engineer who designed a telescope mirror, the programmer who built an atmospheric model, the amateur astronomer who captures a clear image on a cold night, and the student who sees that image for the first time. We are all part of a single, extended effort to listen to the story a distant world is telling. And what a story it is! A tale of invisible heat giving birth to Earth-sized hurricanes, of chemistry painting an entire sky blue, of silent forces that can erase a tempest as if it were a chalk mark on a cosmic blackboard. This is the true gift of Neptune's mystery. It is not just an answer we seek, but the wonder we experience along the way. That wonder is the spark. It is what turns a curious glance at a star chart into a lifelong passion for discovery. When a young person learns that we can track the weather on a planet 4 billion kilometers away, or that a storm larger than our world can come and go like a ghost, it expands their sense of reality. It shows them that science is not a collection of old facts, but an active, thrilling detective story with new clues arriving every time we point our telescopes skyward. The blue giant at the edge of our vision becomes a beacon, calling to the next generation of explorers, engineers, and dreamers. It whispers that there are still magnificent puzzles waiting to be solved, not in the pages of fiction, but right here, in the real and dynamic cosmos we are so fortunate to call home. Could you last even a single second inside one of Neptune's dark spots? The answer is a swift and spectacular no, but exploring that impossibility reveals the staggering power of this alien climate. Let us walk through the experience not as a survival guide, but as a testament to forces beyond human scale. First, you would need to arrive. As your probe descends through the high, blue haze, you might see the dark oval looming like a continent-sized pit. Crossing its boundary would be entering another reality. The pressure here is not like diving into Earth's ocean. It builds from the immense weight of the atmosphere above you, a gaseous ocean thousands of miles deep. Within moments, the pressure would be thousands of times greater than at Earth sea level. It would feel like being at the bottom of the Pacific, then multiplied by 10. Every hollow space in a spacecraft, every air pocket, would be instantly and violently crushed into a solid lump. There would be no dramatic implosion, just an instantaneous, irresistible flattening. Then comes the cold. This far from the sun, temperatures in the upper cloud decks hover around -360 degrees Fahrenheit. That is colder than liquid nitrogen, cold enough to freeze the very air you breathe into a brittle solid in an instant. Your body's heat would vanish into that frigid void faster than your nerves could register the sensation. But this is not a simple, static freeze. You are inside the fastest winds in the solar system. If the pressure did not crush you and the cold did not flash freeze you, the wind would take over. We clock these winds at over 1,200 miles per hour. That is more than 1.5 times the speed of sound on Earth. At that velocity, air is no longer a gentle breeze, it is a solid, abrasive wall. Any object would be sandblasted into microscopic dust by the relentless hail of frozen methane and hydrocarbon particles screaming through the vortex. A sheet of solid titanium would be scoured away like chalk in a hurricane. And then, if you could somehow sink deeper, the environment transforms from lethally cold to infernally hot. As you descend through the dark spot's window, pressure and temperature rise together. Hundreds of miles down, the heat from Neptune's core turns the atmosphere into a superheated, slushy fluid. Here, the chemistry becomes surreal. Scientists theorize that the immense pressure could squeeze carbon atoms from methane molecules so tightly that they literally crystallize, forming a rain of solid diamonds. Imagine a hailstorm of gemstones falling endlessly through a thick, dark fluid of ionized water and ammonia. This is not science fiction, it is a plausible result of the extreme physics at play deep inside the ice giant. For a human, this diamond rain would be irrelevant, as you would have been vaporized into your constituent atoms long before reaching such depths. This entire journey underscores a profound truth about our solar system's diversity. Neptune's lifestyle is one of pure, unadulterated physical extremity. It is a world where the very concept of a surface is meaningless, where weather is a deep-seated geological force, and where the ingredients for precious gems fall as common precipitation. There is no foothold for life as we understand it, no niche for anything fragile or temperate. The giant's beauty is the beauty of raw power and alien chemistry, a reminder that the universe crafts environments not for us, but according to its own magnificent and indifferent laws. To study Neptune is to marvel at a masterpiece of natural engineering that operates on a scale where human experience simply melts away. The dark spots are not cosmic potholes leading to Neptune's molten heart. This persistent image, fueled by science fiction and our own instinct to find familiar shapes in the unknown, is one of the most common misconceptions about these swirling giants. It is easy to see why the mind goes there. Against that smooth blue canvas, a deep, dark oval looks like a puncture, a void where something is missing. But the reality is both more complex and more fascinating. A dark spot is not an absence of planet, it is a difference in atmosphere. Think of it not as a hole, but as a clearing in a fog. From our distant vantage, we are seeing a region where the bright, high-altitude haze of methane ice has thinned or been pushed aside, revealing a deeper, warmer layer that does not reflect sunlight in the same way. It is a window, not a tunnel. The vortex itself is a colossal high-pressure system, a spinning dome of atmosphere that disrupts the usual cloud formation. If you could somehow stand on a platform at that altitude, you would not be peering down a bottomless shaft to the core. You would be surrounded by extremely thin, clear air within a furious cyclonic wind, looking down into a darker but still substantial layer of atmosphere below. The planet's solid core, if it even exists in a traditional sense, is thousands of miles deeper, buried under an ocean of superheated, slushy ices and compressed gases under unimaginable pressure. The dark spot is a purely atmospheric event, a skyscape phenomenon on a planetary scale. Nor are these vast ovals signs of intelligence at work. The idea of alien megastructures or dimensional portals is a thrilling narrative, but it collapses under the weight of simple physics and observation. These features follow predictable, chaotic patterns of fluid dynamics. We see them form, migrate, and dissipate in ways perfectly consistent with the violent but natural weather of a gas giant. Their appearance correlates with Neptune's seasons and internal heat flow, not with any signal or directed activity. The brilliant companion clouds that often frame them are a dead giveaway of natural atmospheric processes where winds force gases upward to condense. Furthermore, if these were artificial constructs or stable portals, they would not exhibit the transient, fragile existence we have documented. They would not drift unpredictably or suddenly vanish when encountering equatorial wind shear. They are enduring because they are natural, born from the same fundamental forces that create hurricanes on Earth, just amplified to an almost incomprehensible scale. Reaching for extraterrestrial engineers might satisfy our desire for cosmic neighbors, but it ironically sells short the breathtaking, inherent drama of the universe itself. Neptune does not need aliens to be awe-inspiring. Its natural weather is alien enough. Letting go of these sci-fi tropes is not about making the universe less exciting. It is about embracing a wonder that is grounded in tangible, discoverable truth. The real story of internal heat driving supersonic winds that sculpt transient hurricanes larger than Earth is more compelling than any fiction because it is real. It is a narrative written in the laws of thermodynamics and fluid mechanics, playing out on a canvas 4 billion kilometers wide. This accurate understanding empowers our curiosity. It directs our questions toward solvable mysteries, like the precise wind shear that destroys a vortex or the seasonal changes that might trigger its birth. It turns our gaze from fantasy toward the next generation of telescopes and potential probes, the real tools that will deepen this story. The dark spots are not holes or gateways, they are profound meteorological statements from a blue giant. They tell us that even in the frozen dark, energy finds a way to express itself in tempests of majestic and fleeting violence. Listening to that natural story and understanding it on its own extraordinary terms is the greatest adventure of all. The investigation into Neptune's vanishing storms is a live broadcast from the edge of our understanding. This is not a closed case in a history book, but an active, unfolding detective story where every new image is a fresh clue. The mystery remains gloriously unsolved, yet we are closer than ever to reading its final chapter. Our tools for this cosmic surveillance are more powerful and coordinated than at any point in history. The Hubble Space Telescope continues its long-term watch, a sentinel in orbit providing the consistent, high-resolution snapshots that reveal new storms and track their migrations. On the ground, an alliance of observatories like Keck and the Very Large Telescope, with their revolutionary adaptive optics, pierces Earth's atmospheric blur to deliver razor-sharp views, filling in the gaps between Hubble's scheduled looks. Inside supercomputers around the world, digital models of Neptune's atmosphere churn through quintillions of calculations, simulating storm life cycles and testing theories of their birth and demise. And waiting in the wings is the James Webb Space Telescope, our soon-to-be-deployed thermal detective that will feel the heat of these vortices and sniff out their chemical secrets. This multi-pronged approach means we are not just watching, we are experimenting and predicting. Each observation, whether from a mountain peak or from space, adds a crucial piece to a four-dimensional puzzle of time, motion, chemistry, and force. The next major discovery could arrive at any moment. It might be a ground-based image catching a dark spot in its final, distorted throes. It could be a Webb temperature map revealing a fatal weakness in a vortex's structure. Or it might be the sudden, unexpected appearance of a brand new storm in a hemisphere we thought was quiet. This constant potential for revelation is what makes planetary science a thrilling endeavor. The narrative is not predetermined. The blue giant still holds the power to surprise us, to defy our models and force a brilliant rethink. Every time an astronomer schedules time on a telescope and points it toward that faint blue dot, they are casting a line into the cosmic unknown, never quite sure what they will pull back. The story of Neptune's dark spots is still being written, one patient, precise observation at a time, and the next line could change everything we think we know. The blue giant's secrets are not locked away in a lab, they are streaming to your screen in real time. You can join this planetary watch from your own home, becoming part of the global network of eyes on the sky. Start by visiting the source, the Hubble Space Telescope's official news center. A simple search for Hubble press releases will lead you to a treasure trove of raw images and detailed explanations, often published within days of a new observation of Neptune. These are not just pretty pictures, they are frontline dispatches from the investigation, complete with annotations from the scientists themselves. For a broader context, bookmark NASA, a solar system exploration website, your digital encyclopedia for every world from Mercury to the Kuiper Belt. Its dedicated Neptune page consolidates decades of discoveries, mission histories, and the latest findings into an accessible, constantly updated portal. To know when to look up, astronomy apps are your essential tool. Applications like Stellarium or Sky Safari can show you exactly where Neptune is in your night sky on any given evening. You simply point your phone at the stars, and the app overlays a map guiding you to that faint bluish point of light. Seeing it with your own eyes, knowing that tiny speck holds supersonic winds and vanishing storms, transforms abstract science into a personal connection. For the most immediate pulse of discovery, follow the astronomers and institutions driving the research. On social media platforms, accounts for NASA, Hubble, the European Space Agency, and observatories like the Keck and the Very Large Telescope regularly share breakthrough images and data as they happen. You might see a brand new photo of a dark spot before it even makes the evening news. Following individual planetary scientists can be even more rewarding, as they often share the excitement, the challenges, and the unanswered questions from the front lines of their work. This transforms your scroll into a learning feed where the latest cosmic weather report sits alongside updates from friends. Cultivating this habit turns passive consumption into active engagement. It is a lifestyle choice, a decision to let your curiosity be guided by the genuine, unfolding drama of exploration. You are no longer just waiting for a documentary to tell you a story that is already years old. You are watching the story being written, one telescope image, one scientist's tweet, one clear night of stargazing at a time. The mystery of Neptune's storms belongs to everyone, and your attention is the most powerful instrument of all. From a single blurry glimpse by Voyager to a relentless watch by Hubble and a global network of Earth-bound eyes, our journey to understand Neptune's dark spots has been a masterclass in patience and ingenuity. We have watched these Earth-sized hurricanes appear from the deep blue haze, churn with impossible winds, and then vanish as if they were cosmic mirages. The core mystery remains as compelling as ever, a testament to the chaotic, inner-driven heart of our solar system's windiest giant. Yet the tools we wield in this quest are no longer passive lenses, they are extensions of our collective curiosity. We have built telescopes that cancel the twinkle of our own atmosphere, supercomputers that simulate entire alien climates, and a space-based observatory that will soon feel the heat of these storms with its infrared gaze. This is not just astronomy, it is a futuristic lifestyle of discovery where anyone with an internet connection can join the planetary watch. So the next time you find yourself under a clear night sky, take a moment to find that faint, steady blue point in the darkness. Remember that 4 billion kilometers away, a world of supersonic winds and diamond rain is writing its own violent, beautiful story. Our own solar system still holds dynamic mysteries unfolding in slow motion, each one a silent call for the next curious mind, the next brilliant instrument, the next great leap in our endless quest to understand the cosmos we call home.